Let us continue homomorphisms and factor rings again. So I hope you have got the concept of kernel. Kernel of a homomorphism is the set of all elements of the domain whose image is additive identity of the codomain. This is what is known as kernel of phi. Let us proceed. Let us deal with the theorem. What theorem says? Let phi from R to R dash be a ring homomorphism and let H equal to kernel of phi. Let A belong to R. Then phi inverse of phi of A is equal to A plus H, which is the same as H plus A, where A plus H and H plus A are equal, is the coset containing A of the commutative additive group H plus. So do you remember what is coset? What is coset?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes. So if at all you are having an element A and you are adding A plus H, what this means? This means you are handling the set of all elements of the pattern A plus small h. And from where small h is to be taken? From capital H. Okay. So the set A plus H is known as coset. Okay. Coset. So we are taking cosets here. And what we say? If H is kernel, in that case, A plus H is the same as H plus A, and it is nothing but phi inverse of phi of A. It is simply phi inverse of phi of A. So you have to keep this in mind. It is nothing but inverse image of A. Phi inverse of phi of A. All right. Then let us go to its corollary. A ring homomorphism phi from R to R dash is 1 to 1 if and only if kernel of phi is singleton 0. So just now I told it to you. Whenever our function is 1 to 1, in that case, kernel is singleton 0 always. Always keep this in mind. If you want to show your phi is 1, 1, this is one tool in your hand. You go with kernel, show that kernel is singleton 0. This will automatically mean that the ring homomorphism is 1 to 1. Followed me? Okay, if not, I will help you. The same example let us come to. You know, its kernel contains singleton 0. Just now we have shown kernel of phi is nothing but singleton 0. Now let us show that this function is 1, 1. How will you show it is 1, 1? So you know better. You start with equal images and reach to the equal pre-images. So what we have is, suppose we have here A, B, minus B, A equal to, suppose we have X, Y, minus Y, X. Now what will happen? These are two matrices. So corresponding places are same. So first row, first column entry must be equal to first row, first column. So I got A equal to X. First row, second column entry is equal to first row, second column entry. I directly got B equal to Y. Now let me confirm my result by equating the next row also. Here I am getting minus B equal to minus Y means B equal to Y itself. and this entry says a is equal to x. So I got this particular. So what I've got, a plus bi comes out to be the same as x plus yi. So what we have shown, whenever images are same, we are getting same pre-images, means my map is 1 to 1. Did you follow? Actually, we used to start from phi of a plus bi equal to phi of x plus yi. Is it so? We used to start like this. And we used to reach to the fact that a plus bi is the same as x plus yi. Got me? Okay, so we have shown that our function phi is 1, 1. So this was just a kind of verification of the corollary. We just verified the corollary. This is not the proof. This was just verification of the corollary. I would like to go back to the same then. So now the concept of factor rings come into picture. Factor ring means quotient ring. So actually we never divide by a polynomial to a polynomial. Never we divide by ring by a ring like this. But how do we take factor then? We collect all cosets. We collect all cosets. So you can see this theorem. Phi again is a ring homomorphism. Kernel is H. Then the additive cosets of H form a ring. That ring is called as R by H. What we do? We take additive cosets of H. That forms a ring R upon H. Now have to have operations on this R by H. Have to get operations. So you have one coset A plus H, another coset B plus H. How do you add them? So H will be there only. You add A plus B. So it is the same as A plus B plus H. Have to define product. So A plus H multiplied by B plus H. So it becomes AB plus H. Did you follow me? The definition goes like, whenever you add two cosets, it is the coset of A plus B. I mean coset due to A plus B. Here again you have A plus H into B plus H. So what do? Actually you multiply A into B and you find the coset of H with A into B. Okay. And you can show that if you have map mu from this quotient ring R by H to the image of R only. How we define this? We define it as mu of A plus H is equal to phi of A, earlier phi. Then it becomes an isomorphism. What is isomorphism? It is homomorphism plus bijective function. Okay, 1, 1 onto homomorphism. So because you are adding this phi of R, image set of R, it automatically becomes onto. And just now we have shown that it comes out to be 1, 1, 1. Why for 1, 1? Because whenever you talk about two cosets, you'll have the same kind of cosets over there. So whenever we'll deal with the example, you'll come to know what I said. Okay. So they have proven it. The proof goes very easily. It's quite simple, but I would like to write it down for you. I'll pen down for you and let you know it. Now, you can come here. This is an example. This is an example. What this example does, the map phi from Z to Zn. How we are defining? Phi of M is equal to R, where R is the remainder of M when divided by N, is a homomorphism. So what will be kernel of phi? Kernel of phi will be NZ. So let us deal with this. Let us deal with this. Okay. Suppose I have phi from the set of integers Z, and suppose I take it as Z5. How we are defining this? How do we define it? Phi of M is equal to R, where R is the remainder of M. So what is going to happen here? Phi of M, sorry, phi of M is equal to R. And what is R? M congruent to R mod phi. So I hope you'll help me. If I start with my integers, if I ask you what is phi of 0? What is phi of 0? Everything is going modulo 5. So what will be the output? What will be phi of 1? What will be phi of 2? Phi of 3? And phi of 4. Hope you are capable. Yes, when I divide 0 by 5, what is the remainder? 0. If I divide 1 by 5, what is the remainder? 1.
1.
Here it is 2. This one is 3. Here it is 4. Now, if I divide 5 by 5, what is the remainder? 5 divided by 5.
0.
0. 6 divided by 5.
1.
It is 1, obviously. We got the strategy now. 7. Phi of 8. Is it right? You check it whether I'm correct or not. Do you agree it is 4? Yes? Okay. Now, my question to you is, what is phi of 123?
Three.
Are you sure? Yes, anybody else?
1.
1 or 3?
Ma'am, it is 3.
Sure, I'm getting 4. Unable to listen to you, Vita. Not getting your words. So it's very damn sure that you divide 123 by 5. The division will be of 120 and 3 will be left back with you. That's damn sure. So phi of 123 is going to be 3. You are very correct. Okay. So I think you got the concept. You got the concept of phi of m equal to r kind of thing. All right. Now, what we mean here, kernel of phi is nz, they are saying. What is the kernel of phi in your case? Kernel means you are collecting all those whose image is 0. So I have given you 2 elements whose image is 0. You tell me the rest. You tell me the rest. Yes. Phi of
10.
yes, very good. 10. Same as yes. What I want, if I divide that number by 5, the remainder should be 0. Means double of 5. So 5, 10. What comes next? 15. Then what? I feel all of you are getting me.
20, 25.
And so on. So can't I write it as kernel of phi? I should have round bracket. Okay, equal to 5n such that n belongs to z. Can I say so? Yes. All multiples of 5. I suppose you are following me. Now, in another example, if I take instead of 5, if I'm taking 17, then what will be the kernel in that case? Value of n, I'm taking 17. What will happen? Yes, my n is 17. So what is the kernel then? Yes, of course. If I divide by 17, I must get remainder 0. What are such elements? 0 is there. 17 itself is there. What is the next one?
34. 34.
Yes, and so on. With plus sign also and minus sign also. So can I shorten this statement? Yes. You have any idea how to make it short? I can write it as 17 and n is collected from Z
Good.
and is taken from Z. So damn sure if I take n equal to 17, kernel will be multiples of 17, but integral multiples of 17. So we write it as 17n. I suppose you followed me. If it was 5, we have already written that kernel is the set of all phi n where n belongs to Z. So what is one more short form? We can write it as 5Z. Can I? Have we used this letter? So we can write it as 5 times Z. Okay. The same way, this can be labeled as what? 17Z. You can label it as 17Z. So coming back to the sheet, you see what is written over here? Phi is from Z to Zn. In that case, kernel of phi is nothing but nz. And if
Madam, Madam, how kernel of 123 is 3?
kernel of
123.
Okay. I didn't ask you kernel of 123. Actually, I tried to talk about how the integers are accommodated in Z5. Here what I said, what is the image of 123? And image of 123 comes out to be 3. What I tried to tell here was, you take any integer, however big it may be, if I divide it by this 5, I get a remainder ranging from 0 to 4 only. So the output will be either 0 or 1 or 2 or 3 or 4. These are the only 5 possibilities. Now, those which are having image 0, they come under kernel. That was the thing. Is there
Okay.
any ambiguity still? I suppose you followed me. Under 5, you'll have some images, but you are collecting only those elements who have image 0. And all those elements, if I collect, that set we always call as kernel. And in this present case, kernel becomes that number times Z. If your number is 5, it becomes 5Z. If you are talking about 17, it becomes 17Z. And now because Pradnya was talking about 123. So if at all you are having from Z to Z 123. In that case, kernel of phi will be, come on, Pradnya,
123.
yes, it will be 123Z. It will be 123Z, of course. So all the multiples, that is what we are talking. What we are talking about? We are talking about kernel of this homomorphism. This is a special case. Homomorphism carries Z to Zn. And in that case, we were concentrating to that n. And we said kernel of phi becomes mz. Okay. Now, once you get kernel, now your responsibility increases. You have to go for quotient ring. And how do you get quotient ring? You can see over here, the quotient ring is Z upon nz. Z upon nz. And already we have shown that ring Z by nz is isomorphic to Zn. Z by nz is isomorphic to Zn. How do you say they are isomorphic? So you need to have some isomorphism. What is that isomorphism? So that isomorphism is nothing but the same just now we discussed. Phi from Z by nz to Zn. What will happen? We are collecting members of nz. What are those? Yes, I would like to do for this Z by nz for you. Okay, this set being smaller, let us deal with this only. This is our favorite set. Can you tell me what will be Z upon, what will be the cosets? What will be the different cosets of this particular? You are finding out cosets of kernel. This kernel for the time being, let us denote by H. What is your set H? Set H contains all multiples of 5. Okay, we labeled it as H. Now, you just tell me what are the different entries because your original set is Z. All of you are quite familiar with Z. Yes. Anybody wants to ask anything? Jyoti?
No, madam.
Okay. Okay. So what we have 0 plus 1 plus 2 and so on. Same time we have -1, -2 and so on also. So this is what we are having. Okay. Now, if I say 0 plus h, I get my h back. So 0 plus h is h itself. If I ask you about 1 plus h, then what happens? What is 1 plus h? So we have to write it. 0 plus 1 gives me 1. 1 plus 1 gives me 2. Sorry. I'm adding to h, not to. So extremely sorry. What is my first element in h? That is 0. So 0 plus 1 gives me a 1. The next entry is 5. 5 plus 1 gives me 6. Next entry is 10. 10 plus 1 gives me 11 and so on. To the left side, I have minus 5 plus 1 gives me minus 4. I hope you remember this. We have done this so many times. Next entry was minus 10. To that you add 1, you get minus 9 and so on. Hope so. Next is 2 plus h. For better understanding, I would have written my h here. Let me write it. What is our h? 0, 5, 10, and so on. And before it, it is minus 5, minus 10, and so on. Do you agree? This is our h, all multiples of 5. Sure. And to that, I added 1. Now I'm adding 2 to that. So if I add 2 to that, what do I get? And so on. I'm adding 2 to this. So I got minus 8. This will be minus 3. 0 plus 2 gives me 2. 5 plus 2 gives me 7. 11 plus 2 gives me 12. And so on. I suppose you are getting. Next, let me go to 3 plus h. Yes, would you like to prompt me?
Minus 7.
Yes, of course, this will be minus 7. Next,
Minus 2.
next,
3.
yes,
8.
next,
13.
yes, and so on. Okay, and let us have our last set. So I would like to go with this particular one. Sure. So what is my last set? It will be 4 plus h. Just prompt me. Minus 10 plus 4. How much?
Minus 6.
Yes. What next? Minus 5.
Minus 1.
Yes, very good. 0 plus 4.
4.
Yes. What next?
9.
Yes.
14.
Yes. And so on.
14.
Yes, very good. Now let us see what we are getting. I started with 0, then 1, then 2, then 3, then 4. Again, I see 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So all the next terms I'm getting. Let us see what happens before 0. So I got minus 1, minus 2, minus 3, minus 4, minus 5. Minus 6, minus 7, minus 8, minus 9, minus 10. Means nothing is missing. I'm getting my z back. If I get complete z back, we say all the elements are exhausted. And if all the elements are exhausted, the only cosets with me are 0 plus h, 1 plus h, 2 plus h, 3 plus h, and 4 plus h. Got me? Have we done this in group?
Yes, ma'am.
Okay. So what you do is you just collect all those sets under a set. Just a minute, I will not write it. Okay. So let me collect all of them under a set. First set was 0 plus h. Second set was 1 plus h. Third set was, yes, come on.
2 plus h.
2 plus h,
Next is,
3 plus h,
yes.
4 plus
And last is 4 plus h.
4 plus h.
Only cosets with you. You collected all the cosets under a set, and what this set is labeled as z upon what? Nz. What you did? You collected it as z upon nz. Okay, this is what we are saying. This is nothing but your quotient ring. This is your quotient ring. So my question to you is, how will you add any two of them? If I want to add a 2 plus h and 4 plus h, what will be their addition? Because if you want a ring, you need to have two operations, one of addition, the other of multiplication. So how would you add this? Come on. It is but natural. H remains as it is. I have just now shown you the definition. And we have to go with 2 plus 4. What is 2 plus 4?
6.
6. But we have to deal with our 5. So 6 with respect to 5 gives me what?
1.
1. So this becomes 1 plus h. Followed me? This is simply 1 plus h. Now you got the idea. So if I ask you about multiplication, then I think you can immediately answer me. If I ask you what will be 2 plus h into 4 plus h, how much? Yes, come on. I think you have completed your answer. I take too much time to write. You know? So what it will be? Yes, what should you do? 2 4s are
8.
3 plus h.
3. 3 plus h.
yes, very good. So the answer is going to be 3 plus h. So it is back in your set. So you can see that this particular forms a ring under addition and multiplication defined this way. So it's a ring. Now your question says show that this is isomorphic to Zn. So how would you go for Zn? How would you define isomorphism? So they are saying that performing the corresponding operation in Z. Okay, the theorem also shows that this ring is isomorphic to Zn. So here they are giving it is isomorphic to Zn. This one. This one. So what is the map? What is the isomorphism? From R by H to phi of R, if you go, you are taking mu of A plus H as phi of A. Mu of A plus H as phi of A. So here you can see mu of, let me write like this, mu of 2 plus H. It will be equal to phi of 2. What is your phi of 2? Remainder when divided by 5. So 2 divided by 5, it is what? 2 only. So mu of 2 plus h you are defining as 2. Mu of 1 plus h will be 1. Mu of 3 plus h will be 3 and mu of 4 plus h will be 4. So that will work. I hope that will help you. Okay.